In this video we'll review how to write simple rotation matrices and how to concatenate multiple rotation matrices together to get complex rotations. This will help us express the position of this point P from NO in different coordinate representations. Here we just have a 3D view that will be helpful as we visualize the multiple rotations in this problem. To get started, let's introduce some unit vectors that are fixed in this reference frame N. Here we have nx, ny, and nz, all orthogonal to each other. One way to measure the position of this point P from NO is to use measures along nx, ny, and nz. So if we had a scalar distance x measured along nx, and a scalar distance y measured along ny, and a scalar distance z measured along nz, then we could write the position vector to P from NO as x nx plus y ny plus z nz. As we'll see in some later problems though, it could be useful sometimes to express this position just in terms of a unit vector that points from NO to P. So that would sort of look like some distance rho in the direction from NO to P. And we'll call this BZ for now, and you'll see why once we introduce some additional frames. So first, let's observe that P can be projected down onto this nx, ny plane, and that projection point is called Q. And there's a line going from NO to Q. So we could assign a frame that we'll call A, with a unit vector AY that is pointed from NO to Q, and a unit vector AZ that's aligned with NZ. And we can say that frame A and frame N are initially aligned, but then frame A is rotated about the vertical by an angle theta. And notice it has negative NZ sense because this rotation is clockwise. So by right-hand rule, that's actually a negative NZ rotation. So in 3D, we're saying that this frame A is initially aligned with N, but then as we increase theta, it rotates about the vertical with minus NZ sense. And so the angle theta is this angle right here between the green line and the green unit vector. Next we'll assign a new frame, which we'll call B, and B is going to be initially aligned with A, but then also rotated. So we'll introduce an angle here which is called phi, and phi is the angle of rotation about AX or BX. And it actually has negative BX sense, because you'll notice to go from this orientation to this orientation, it's a rotation that's clockwise about BX. So going back to our 3D view, we have this frame B now, which is initially aligned with A, but then it's going to rotate about these red unit vectors, which are AX and BX, with negative sense because it's clockwise. And the angle here is between this vector and this vector. That angle is called phi. So as we increase and decrease phi, we get this frame B with BZ pointing from NO to our point P. So now what we'd like to do is figure out how our x, y, and z measures, which we introduced earlier, are related to these rho, theta, phi measures that we just introduced. And the key insight is just to realize that what we want are the nx, ny, and nz measures of this vector, which we can get by dotting. And so then the question is, how do I find these dot products? How do I actually figure out what is bz.nx and bz.ny and bz.nz? So if we could write the rotation table relating frame B and N, then we can recall that the entries here are the dot products. And so this third column here gives us BZ in terms of NX, NY, and NZ, and hence it gives us those dot products. But forming this rotation matrix all in one go is relatively difficult because of this geometry. Instead, let's see if we can form it as the concatenation of two simple rotations. So first let's look at the rotation table that relates frame N and frame A. Just to get going, it's nice to start with the easy ones. We'll notice that AZ and NZ are always aligned, so we can say that their dot product is always going to be 1. Similarly, AZ is up out of the ground plane, but NY and NX are both in the plane, so the dot product there will be 0. And similarly, NZ is vertically up out of the plane, but AX and AY always remain in the plane, so the dot product there will be 0 as well. For these other dot products, it can be somewhat difficult to look at this 3D picture and figure it out. So it can be helpful to redraw the frames in 2D. So here we have NY to the right and NX down. So we're basically just looking down on this from above. And then we have frame A with AY and AX as well, and theta is labeled here. And we'll recall that this angle is also equal to theta. So now it's relatively straightforward to look here and say, okay, the angle between AY and NY is theta, so their dot product will be cosine of theta. Similarly, the angle between AX and NX is theta, so their dot product will be cosine of theta. And now nx.ay will actually be the cosine of 90 minus theta, which happens to be equal to sine of theta. And finally, to get ax dotted with ny, it can be helpful to sort of imagine projecting ax onto this line, and we can see that this quantity here is sine of theta, and it's in the minus ny direction. So we have minus sine of theta. Next, we'll do the rotation table relating frame A and frame B. Just like before, it can be helpful to redraw this in 2D. So now we're sort of looking at it from this direction. So AY is to the right, AZ is up, and then frame B has been rotated by this angle phi. And we'll remember that this angle here is also phi. So now we can start filling this in and say, okay, AX and BX are always aligned. And then as we're starting to notice, if we have a 1, the column and row that 1 is in needs to have zeros. And then we have by.ay, so we look over here and say, oh, the angle between them is phi, so we're going to have cosine of phi. Similarly, the angle between BZ and AZ is phi, so we'll have cosine of phi here. And then we have BZ dotted with AY, so here it's this interior angle, so we'd have cosine of 90 minus phi, which is equal to sine of phi. And then finally we have BY dotted with AZ. So again, it can be kind of helpful to mentally project BY onto this line that AZ lies on, and then say, okay, this distance here is sine of phi, but it's in the minus AZ direction. So there we have the two rotation tables that relate N and A, and that relate A and B. So to find the rotation table relating frame N and B, we just need to take the tables that we just found and multiply them together. It's important to note that they need to be in the correct order, so we have N to A and then A to B. Notice that the A's are together on the inside here. And so we take these, and notice that I am using this notion of rotation table and a matrix interchangeably. So rotation table, rotation matrix, same idea. I'm not going to go through all the arithmetic of multiplying these, but please do make sure that you are able to multiply these two matrices together and get this result. Now we'll just label this matrix with our table notation just to sort of make sure that we remember what we're doing. So now we're finally ready to relate the x, y, z measures of this position with the rho, theta, phi measures. So as we said before, x is going to be this position vector, rho bz, dotted with nx. That gives us the nx measure of this position vector. So looking over here, we have bz.nx is equal to sine theta sine phi, and we're multiplying that by rho, so we get this quantity. Similarly, we'll have y is equal to rho cosine theta sine phi, and finally z is equal to rho cosine phi. It's worth reiterating one more time that these relationships between the Cartesian xyz values and the spherical coordinates are not the same as some of the spherical coordinates you may have seen in other classes. And that's partly because we chose to define phi from the vertical instead of from the horizontal, as is often done. But as you'll realize as we go through this class, selecting measures is purely an arbitrary choice, so there's nothing wrong with us having chosen spherical coordinates like this. It will just change what our equations look like, but it won't change our ability to analyze our systems.